Think about what happens when you open your phone. You type 2 letters into a search bar, and it finishes your sentence. You swipe right, and a match appears instantly. Your social feed refreshes before you even finish pulling down the screen. Apps handle this global workload by relying on a specific type of engineering. They don't survive a massive surge of traffic by simply using bigger, faster computers. The challenge is the sheer volume of information. A beginner programmer might try to solve a problem by looking through a list of items one by one, but when you have a billion users, checking every single name would take hours. A software architect avoids this by using data structures. These are specific organizational blueprints that allow a computer to bypass the heavy lifting and skip past the vast majority of the data. These specific arrangements are the reason we can turn billions of data points into the tools we use every day. To see how this works, look at how a streaming service loads your profile. It has to find your specific account out of over 260 million active users. If the app kept everyone's name in one giant list and checked them one by one until it found yours, you'd be staring at a loading screen for several minutes. Architects use a structure called a hash map. It runs your username through a math formula, converting your name into a specific grid coordinate. Since the system knows your exact coordinate, it bypasses the list and jumps directly to your data. This is a deliberate trade-off. Building that coordinate grid uses a lot of digital storage space, but engineers use that memory to guarantee the app stays fast even as more people join. Now imagine a social media app trying to figure out the top 10 trending topics globally out of a billion posts happening every minute. Mathematically sorting a billion items from most popular to least popular would freeze the entire system. You can't stop the internet every time a user refreshes their page. The solution is a min heap, a VIP list with 10 slots. Instead of sorting a billion posts, it only monitors these 10 items. When a new popular topic arrives, it kicks the lowest item off the VIP list and takes its place. By ignoring everything that isn't a top 10 contender, the system answers a massive global question using almost zero memory. A different problem arises when concert tickets go on sale. Automated bots will try to purchase thousands of seats in a single second, locking out real fans. Managing these sudden surges of traffic is a central crisis for ticketing companies, often leading to site crashes and legal investigations. To stop the bots, architects use a pattern called a sliding window. It acts like a digital bouncer at the front door. The system monitors a narrow time frame, like the last 60 seconds. If it counts too many requests from one user, it blocks them. As the window slides forward, older requests fall out of view, resetting the user's limit so they can try again. This digital bouncer, which engineers call a rate limiter, protects the system by controlling traffic in the present moment, without needing to store the entire history of the internet. Success in high-level tech comes from recognizing which mathematical pattern matches the physical constraints of a real-world problem. Once you recognize these patterns, you'll see them everywhere. The same sliding window used to block ticket bots is also used here, at the New York Stock Exchange, to track the rolling averages of stock prices. In this world, there are no perfect solutions, only trade-offs. You can buy speed by using more memory, or you can save memory by focusing on a limited set of data. The next time an app responds to your touch instantly, you'll know it's the result of a perfectly chosen blueprint executing its trade-off. Subscribe to see how we build the rest of the digital world.